In this, our final week of the course, we're going to continue with our study of eigenvalues and eigenvectors. To resume, we're going to look at a matrix and just remind ourselves about what eigenvalues and eigenvectors mean, or what one interpretation of them is. If we think of matrices representing linear transformations, then eigenvalues and eigenvectors provide us an alternative way to summarize the effect of that linear transformation. For instance, this matrix here, A, can be thought of something that transforms vectors xy into new vectors in xy. So a transformation from 2 dimensions to 2 dimensions. And we'd apply that transformation by doing matrix multiplication between the matrix here and the column vector. And just looking at this matrix, you can see, well, we're going to get some weird like 0.9 x's and 0.1 y's added together and sort of mismatch of that. It's hard to say what that means, and it's certainly hard to imagine if we did that more than once, how complicated that would get. The eigenvalues and eigenvectors give us another way to look at this that is easier to understand. Specifically, this matrix has the following eigenvalues and corresponding eigenvectors. It has a first eigenvalue of 1, corresponding to a matching eigenvector of 1, 1. And again, here we switch between column vectors and row vectors interchangeably, mostly because of typesetting and page spacing. Having been told that lambda equals 1 with a corresponding eigenvector of 1, 1 here, we can immediately say that any vector that is parallel to the vector 1, 1, so I will write it in the same style there, and by that, again, parallel, exactly what you think it means, so 1, 1 itself, or 5, 5, or minus 10, minus 10, it can be the negatives as well, will be scaled by it'll be scaled by the eigenvalue, so by 1. Or, because scaling by 1 doesn't mean a whole lot, or will be unchanged. Now, it's unchanged specifically because of this 1 value. If we compare and contrast with the second eigenvalue, we can write out exactly the same form of sentence, that when we apply this A matrix, which again, for an arbitrary x and y looks pretty complicated, if we get lucky and we have a vector that's parallel to this eigenvector, and a vector parallel to the vector negative 1, 1, and again, e.g. 1, negative 1, 1, negative 5, 5, 10, negative 10, it will be scaled, no comma, will be scaled by its corresponding eigenvalue, which was 0.8. So this is going to tell us all the information we need to know about what the A transform does in a different format, in some way easier to parse format than the matrix form. And remember, this is enough information to transform any input vector from R2, because these two elements here are a basis for R2. And we're going to explore that concept further on during this week. But the idea is, if you had any vector, v in R2, because these are a basis, v has some combination of the first vector and some multiple of the second vector. These are not the eigenvalues anymore. This is just, how do I get to this vector? Well, follow this direction for a times and follow this direction for b times. And then the a of v will be the same as the transform of each one of these things separately. And then a applied to this vector is going to be just a scaling, and a applied to this vector is just going to be a scaling. And so that's going to be much easier to compute than the general AV that we see in this form here. More illustrations will follow. It's helpful at this stage, I think, to remind ourselves what the eigenvalue and eigenvector calculations are. Just remember that the original eigenequation, eigenvector, eigenvalue equation technically, but that gets too long to write. The eigenequation is, for a matrix B here, B times some vector V is the same as a scalar times that same vector V. So B scales the vector V by lambda is another way to say that out loud. Then we did some work with that equation, we shuffled things around, and we came up with the eigenvalue condition, which is that B brought the lambda over, but we had to multiply it by an identity matrix to make this matrices times matrices. That new matrix had to be non-invertible, so it had to have a determinant of 0. So we're just going to apply that here and see what we get. So remember, vertical bars can also represent determinants. That is the same as 7, 3, 3 minus 1. And this week, I'm just going to slide the lambdas along the diagonal with the negative signs without changing the color. We've seen that enough times now, hopefully, to remember what that minus lambda I here does is all the way down the diagonal, it subtracts a lambda. We then do our determinant calculation, the cross multiplying here for a simple 2 by 2, and we get 7 minus lambda times negative 1 minus lambda minus 3 times 3 is minus 9. And that's the determinant part. We're now going to set that equal to 0 to define our lambdas. Now we should definitely expand that out. And that'll be negative 7 plus a lambda minus 7 is minus 6 lambdas plus lambda squared minus 9 still equals 0. We'll tidy that up. That is lambda squared minus 6 lambda and minus 16 still equals 0. That's nice quadratic form, and we can see that minus 8 and plus 2 will be factors for that. And so lambda 1 equals 8, lambda 2 is negative 2, are the eigenvalues for B. All right, so that's fairly straightforward. This is also an opportunity, though, to think about the general case for eigenvalues, and we're going to do that on the next page. Something we actually haven't asked yet is how many eigenvalues are there? Well, let's start with our 2 by 2 matrix that we just looked at, and let's do the A minus lambda I form that we would have typically done. A is our go-to matrix for generic matrices. So if we had a generic 2 by 2 matrix here, and we slide the lambdas, minus lambdas down the main diagonal, try to make the lambdas look like lambdas, there we go. That would be A minus lambda times D minus lambda. And don't worry, we're not going to solve this in general. The key thing to note is that this is going to be a polynomial in lambda. And specifically, what degree is it? Well, we're always going to multiply that down the diagonal, and there's a lambda in every term down the diagonal, so we're going to have specifically a quadratic, or degree 2. And as you know, degree 2 polynomials will have 2 solutions. We're going to have 2 roots to that polynomial, and the roots for that polynomial means that you're going to have 2 eigenvalues. Now, it's worth noting, of course, we can get real or complex, and possibly repeated. Remember, if we have a quadratic, we can either have repeated real roots, 2 complex roots, 2 real roots, but at the end of the day, there are 2 numbers that we get back from solving a 2 by 2 equation. Well, the next question is obviously, hey, if we had an n by n matrix, what would we get? Well, the form of the determinant is the same. We still need the determinant equal to 0. The difference is now the matrix is going to be bigger. I'll just put little subscripts here. If we think of the diagonal elements here, and then there's going to be stuff, stuff, stuff everywhere else. It doesn't really matter what's in there for the form we're looking at, though. At the end of the day, we're going to have a stack down the diagonal in an n by n matrix of minus lambdas all the way down the diagonal. And that's going to give us, not surprisingly, again, a polynomial in lambda. And it's going to be this time of degree n. Well, we're going to take advantage of a little thing I like to call the fundamental theorem of algebra. The fundamental theorem of algebra that says an nth degree polynomial has n roots. Now there's some fine print here. It's n complex roots, and complex includes real as possibilities. There's some asterisks there about the multiplicities and repeatedness, but at the end of the day, we are going to get n roots to this polynomial, which means that this has an n by n matrix, has n eigenvalues. Possibly repeated, possibly complex, but basically for a 3 by 3 matrix, you should be able to find 3 eigenvalues. For a 10 by 10, you'll find 10 eigenvalues. And the gateway for that is that determinants always involve these multiplications with the lambdas, and those always lead to polynomials. And based on that, we give these polynomials a name. Specifically, this part of the equation, determinant of a minus lambda I, turns into a polynomial every single time of degree same size as the matrix, and we give that the name characteristic polynomial. And it's of interest, of course, because the roots of the characteristic polynomial, that's what we get when we set this equal to 0 and solve for lambda, are the solutions to this. And those same lambdas are the eigenvalues of the matrix. Well, that's because this is exactly what we meant by our eigenvalue condition. And so you can think of it as having a polynomial that comes out of the determinant and we're finding its roots, or you can think of it as the eigenvalue condition that we worked so hard to build. They're both going to mean the same thing. To illustrate that terminology, what was the characteristic polynomial for b? Well, we had not b, but the determinant of b minus lambda I, when we did some work, ended up being lambda squared minus 6 lambda minus 16. That's b's characteristic polynomial. Characteristic polynomial. Again, nothing new happening here. It just helps when we have this intermediate step along the way of, gosh, do we always get a polynomial? Yes, we do. And should we give it a name? We absolutely should. Call it the characteristic to go with our translation of eigen, meaning characteristics of a matrix as well.